Yengulalp, and the title of their talk is Completeness Properties and Topological Games.
All right, thank you. Well, thanks very much to Zichin for the invitation. I think he might be coming back. I'm really happy to be here. I'll be talking about completeness properties, and since it's a birthday party, I brought games as well. Let me start somewhere familiar. What do we mean when we say a topological space is complete? Well, for metric spaces or metrizable spaces, we mean that there's a compatible metric in which every Cauchy sequence has a convergent point in the space. If you want to generalize completeness to more general topological spaces, you might replace sequence with something more general. So you might talk about convergence of filters or something like that in the space. Maybe I'll come back and take a slightly different perspective. It's well known that in the class of metrizable spaces, the completely metrizable spaces are exactly those that are G delta in any metrizable extension. So in particular, a metric space would be completely metrizable if it's G delta in its metric completion. Well, if I expand to Tikhonov spaces, then the check complete spaces are exactly those that are G delta in any compactification, or equivalently, G delta in the stone check compactification. So G delta is sort of essential in these notions of completeness, and it's immediate that, of course, these properties would then be hereditary to G delta subspaces. And if we discuss some other general topological completeness properties, it's natural then to ask if G delta subspaces enjoy that property as well. Okay, so I'll introduce another generalized completeness property. First, a bit of notation. I'll use this closure subset relation a lot. So if I have two open subsets of a topological space, I say V is closure less than U if the closure of V is contained in U. So that when I talk about maybe filter bases or something, I can refer to them as directed sets under that relation. So for example, a regular open filter base is a collection of open sets that has the property that given any two in the filter base, there's a third whose closure is in the intersection. I'll just say that a regular open filter base is a collection of open sets that's downward directed by this closure less than order relation, I should say. Okay, so de Groot introduced a class of generalized completeness properties called the Amsterdam properties. The food truck outside had no idea what I was talking about. They're not aware of these things, which I don't know what's going on with them. But subcompactness is the weakest of those properties, and you see some sort of convergence definition here. A space is called subcompact if it has a base, we'll call it a subcompact base, such that anytime you take a regular open filter base or a directed subset of that base, it has non-empty intersection in the space. So completely metrizable spaces, also locally compact spaces, have subcompact bases. So the class of subcompact spaces includes these two nice classes of complete spaces. Subcompact also enjoys a lot of preservation properties. Open subsets of subcompact spaces are subcompact. Finite unions of subcompact spaces are subcompact. The product of any collection of subcompact spaces is subcompact. And from the previous slide, I claimed that it's natural to ask whether or not G delta subspaces of subcompact spaces are subcompact. Compact spaces are certainly subcompact, so it's also a weaker question is whether check complete spaces are subcompact or not. So these two questions are still open in general. I want to talk about the partial results of this question and then return back to the bigger question to sort of motivate a more recent completeness property that I studied. Okay, so Von Mill and Kachuk proved that a special class of check complete spaces are subcompact, so-called K-separable spaces. K-separability is a generalization of separability. A space is K-separable if it has a dense subset that is the countable union of compact sets. In fact, they proved that if you have a check-complete space that has a dense subset that is the countable union of closed subcompact subspaces, then it is subcompact. And Yengulalp took this result and proved that all monotonically normal check-complete spaces are subcompact. And further, just recently, Kachuk showed that G-delta subspaces of this special class of compact spaces, Eberlein compact spaces, are subcompact. We just submitted a joint paper with Vladimir, Gila Niknajad, and myself, and this is included in that. And we also talk about some other completeness properties that I won't get to in today's talk. So these are all addressing our check-complete spaces subcompact question. What if I go back to just the original question about are G-delta subspaces of subcompact spaces subcompact? So I'll try and prove it, and I'll likely fail by the end of the slide, but I want to use this as sort of a motivation for something else. So I've got a perfectly good dry erase board here, so let me draw a space X that is subcompact, and I'll fix a subcompact base for X. And let me take a G-delta subspace Y. Okay, so Y is the intersection of open subspaces of X, UN, and okay. Let's suppose that I wanted to prove that Y was subcompact. Well, I've got to define a subcompact base for Y, and I'd like to use the ingredients I'm given, so I'm probably going to use the subcompact base for X to try and do that. So I fixed the subcompact base. Remember, B is a collection of open sets, a base for X, such that any closure less than directed set has non-empty intersection. The most natural thing to do is to intersect down onto Y, and at least I get a base for Y, so that's a good start. But it's not going to be a subcompact base, or else it would be hard to prove. But let me say some things about what we're trying to get after. So if I wanted, let me write up here. So if I wanted this, B sub Y to be a subcompact base for Y, then I'd like, anytime I take a directed collection in BY, and here closure directed is a subspace closure, every time I take a directed collection like that, I get non-empty intersection maybe by reflecting back up to X, creating a directed collection there in the B base, getting non-empty intersection and concluding my proof. So to do that, I would need to sort of start with open members in BY, associate to them some member in B. Of course, that's not going to be a one-to-one process, and what do I need to include in this selection to get my proof to go through? If I manage to come up with some suitable selection, I guess this would be more like B to B hat. Does a directed collection in B sub Y go to a directed collection in B? Well, probably not, but even if I arrange that would happen, a non-empty intersection up here in X doesn't guarantee a non-empty intersection down on Y unless this intersection actually meets Y. So there are a lot of places that the proof goes wrong, and not even just down here, but I'll mention one thing about subcompact bases. When you're trying to prove stuff about subcompactness, the bases are really finicky. So Bill Fleister and I were first studying subcompactness in 2013, and we have a whole section in our paper that's called subcompact bases are fragile. There's a lot of stuff that you want to say about subcompact bases you just can't. Like, for example, I might say I've got a subcompact space X, fix a subcompact base where the sets are regular open or something like that. Well, you can't do that. And there's lots of other things that you can't do that sort of sets you up nicely for a proof afterwards. Okay, so I can't prove that G delta subspaces of subcompact spaces are subcompact, but what can I do? Same setting, I'm going to start with a subcompact base for X, and I'm going to consider a G delta subspace, Y, and I fix that, trace BY base for Y, and I'm going to switch perspectives. I'm going to think of the base for X as being an index set for the base on Y. So I'm going to rename the members of B. I'm going to call them P and Q, P's and Q's, and I'm going to imagine those as indexing the members of the BY. So the base for Y is now a bunch of BPs. And BP can equal BQ for P not equal to Q, because many members of B might trace down to the same member of BY. Okay, and then what I'll do is I'll define a relation on B, which is now serving as an index set, and it's going to include the original closure relation on B. So I'm going to declare P, I'll say way below Q, borrowing some language from domain theory, if the closure of P is inside Q. Number 2 is saying that P is closer to Y in the following sense. Either P is already a subset of Y, in which case I'd say P is way below Q just if the closure of P is contained in Q, or if P isn't contained in all of the UNs, P is not contained in Y, it's contained in strictly more of the UNs than Q is. So I'm not sort of considering the closure relation on BY directly. I'm defining a new relation up here on the index set for the BPs. Okay, so what do I get from this? Well, I still have that the BPs form a base for Y. And if I take a directed collection of the indices, or a directed collection of the base for X, and this time directed by the new relation way below, then this is what happens. Either P, well first actually, P is directed by closure relation, because that's included in the way below definition. So I know that the intersection of P is non-empty up in X, because that was a subcompact base. But also, one of two things happens. Either P has a member that's a subset of Y, in which case the intersection of P is in Y, and that's kind of what I want. Or it has members, P has members that are in arbitrarily high UNs, which means that any point in the intersection of P has to be in all of the UNs. So what I've gotten now is a directed collection in B maps to a collection of BPs with non-empty intersection. So not quite what I wanted, but it's another thing. I mean, I'm saying that G delta subspaces of subcompact spaces have something else going on. You can create this index set that sort of has a convergence mapped out like this. Well, if you're familiar with domain representability, what I really argued here, without a lot of detail, is that G delta subspaces of subcompact spaces are domain representable. I'll put a precise definition here in a second, but in this way I'm introducing sort of another well-known completeness property from the G delta problem. So let me just restate subcompactness really quickly so that I can give you a precise definition of domain representability. These three things are just redundant on this slide. In a subcompact space, this closure relation is transitive and anti-symmetric just because it's defined as sort of a subset. It's coarser than subset. If the closure of B prime is in B, obviously B prime is a subset of B. This is sort of a statement of regularity here. If you have a point in the space and you consider all the B's that contain it, it's going to be downward directed by the closure relation. And then here's the completeness of subcompactness restated. So this is this is a definition that Bill and I were using for domain representability. We proved that this is, if you know what domain representable is, then this is equivalent characterization, and this is what was happening in the G delta proof. So we say that an index set Q together with a relation way below and a map B represents a space if the following conditions hold. And these are sort of just a transfer of the conditions on the previous slide. One small stipulation, I'm reversing the order here because sort of higher indices should map to smaller sets, but other than that, this is effectively what we were able to set up for the G delta subset of the subcompact space. So we proved that this is equivalent to domain representable by using an argument of Bennett and Lutzer that they showed subcompact spaces are domain representable using ideal completions. It's not clear in the beginning whether you can arrange that the B map is 1-to-1, kind of like in the G delta argument. You can't suppose that indexing is 1-to-1, but I showed later that you can do that for regular spaces. It's still open for Hausdorff spaces as far as I know. So let me just say a couple things about domain representability. Key Martin was the first person to study this as a topological